So this brings us to the second half of this chapter, and we're going to talk about what are some of the properties of solutions. What is something that is different about a solution than it would be if you had the pure solvent? So, for example, if you take water and you add sugar to it, is it different or is it the same as pure water? Well, it turns out that there's a few things that are going to be different if you have a solution versus the pure solvent. These are called colligative properties, and the reason why they're called colligative is that they're properties that depend on the concentration. And so colligative means like collective. So it matters on how many solute particles you have, and it doesn't really care about identity. So it depends on the concentration, but not identity. So if I put sugar in water, or if I put ethylene glycol, which is antifreeze, if I put that in water, these properties, they'll act the same. It doesn't care if it's sugar or if it's ethylene glycol or if it's salt or if it's something else. Now, there is a little caveat with the salt, which I'll talk about in a little while, but it depends on the concentration, not the identity. So that's why it's called colligative properties. And these properties are the following: vapor pressure lowering. So a solution will have a lower vapor pressure than the pure solvent. A freezing point depression, meaning that a freezing point of a solution will be lower than the freezing point for the pure solvent. This is why we put salt on the streets in winter. You put salt on ice, it's going to make a solution that has a freezing point lower than 0 degrees Celsius, and so it will lower the freezing point. Similarly, why we put antifreeze in our cars is because that will lower the freezing point of the solution in your car. It won't freeze at 0. It'll have to get colder to freeze it. And then by the same token, boiling point elevation. So a salt solution will have a boiling point higher than the normal solvent. So if I have a salt solution, it will boil hotter than 100 degrees Celsius, an aqueous solution. And similarly, even though it's called antifreeze, the ethylene glycol in water will also raise the boiling point. So what it does is it extends the liquid portion of the phase diagram. It'll freeze at a lower temperature and boil at a higher temperature. So it'll be liquid for a longer temperature range. And then finally, there's something called osmotic pressure, which I'll talk more about when we get to it. These are 4 properties that are different for solutions than they are for pure solvents. So let's talk about them in order. So vapor pressure lowering. Well, the vapor pressure of a volatile solvent will be reduced by adding some kind of solute. So you can see here in the picture, this is an aqueous solvent. So this is pure water, and this is water with maybe sugar in it or something. And you can see that the number of molecules in the vapor are smaller than they were in the pure water. And so what's happened is that the vapor pressure has decreased. This is because the solute molecules decreases the surface area available for solvent molecules, and so fewer of them will evaporate. So the rate of vaporization decreases, but the rate of solvent condensation remains the same, and so overall there's fewer gas molecules in the vapor. So putting some kind of non-volatile, meaning not another liquid that has a high vapor pressure, but something like salt or sugar or something like that, putting it into a solvent will reduce the vapor pressure. So of course there's an equation to go with it. The vapor pressure lowering is a colligative property, and the vapor pressure is related by Raoult's law. Raoult's law says that the vapor pressure of the solution, let's get my thing. So vapor pressure of solution is equal to the vapor pressure of the pure solvent times the mole fraction of the solvent. So P solution is the vapor pressure of solution, X solvent is mole fraction of the solvent, and P naught is the vapor pressure of the pure solvent. And this should make sense because the mole fraction should always be less than 1. And remember that if you're talking about the mole fraction of the solvent, the bigger the mole fraction of the solvent, the less solute there is. And so the closer the vapor pressure of the solution is to the vapor pressure of the pure solvent. So the smaller that X solvent gets, then the bigger X solute gets, right? Because they total 1. So the smaller mole fraction of solvent gets, the bigger the mole fraction of the solute is. So in other words, more concentrated. So as X of solute gets bigger, it's going to lower the vapor pressure more. So as X of the solvent gets smaller, the mole fraction the mole fraction of solvent gets smaller, the vapor pressure will get smaller. It gets lowered and lowered and lowered more the smaller the mole fraction of solvent is. And remember that mole fraction is always less than 1, so P solution will always be less than P solvent. So let's look at an example. The vapor pressure of water is 17.5 torr at 20 degrees Celsius. If you keep the, now vapor pressure will change with temperature, but they're just telling you that's just kind of informational. And then they're telling you if you keep the temperature constant and add glucose to the water so that the mole fraction of the water is 0.8, or in other words, the mole fraction of the glucose is 0.2, then what will the vapor pressure of the solution be? Well, it'll be the mole fraction of the water times the vapor pressure of pure water. So it will be 14 torr will be the vapor pressure of the solution. So it definitely has decreased. And again, notice that if we increase the mole fraction of the solute, the bigger this gets, the smaller this gets, and so this lower the vapor pressure of the solution will get. And this is a colligative property because it doesn't matter what the solute is, only what the concentration is. It doesn't matter that this happens to be glucose, but it's the mole fraction of the water. If you put ethylene glycol in there, it'd be the same. If you put salt in there, it'd be the same, although it'd be slightly different depending on, we'll talk about that with salt in a little while. All right, so here's one more example. This just kind of combines a few things that we've looked at so far. Okay, so glycerin is a non-volatile, non-electrolyte. And that's important, as we will talk about later. So just keep that under your hat for a second. Non-electrolyte means it doesn't dissolve and it doesn't give ions. So it'll stay as a compound. And that, like I said, that'll be important in a little while. It's non-volatile. If it were volatile, we would get into all kinds of other things. So they're just clarifying that it's non-volatile. So let's calculate the vapor pressure of a solution made by adding 65 grams of glycerin to 500 grams of water. And they're telling us that the vapor pressure of pure water is 23.8 torr. So remember that the vapor pressure of the solution will equal the vapor pressure of the pure water times the mole fraction. So what we're having to do, they didn't give us the mole fraction directly. What we have to do is find the mole fraction. And this is the mole fraction of water, remember, or water, because water is the solvent. So water is A and glycerin is B. So we need the mole fraction of the water. So remember what mole fraction is? Mole fraction is moles of water divided by total moles. So we're going to need to convert 500 grams of water to moles, and then we're going to have to convert 65 grams of glycerin to moles, and then we can plug it in this to find the mole fraction. In glycerin, I've given you the molecular formula for glycerin. So we convert 65 grams of glycerin to glycerine or glycerin? Glycerin. 65 grams is equal to 0.706 moles. 500 grams of water is equal to 27.8 moles. So the mole fraction of water is going to be 27.8 divided by the quantity, 27.8 plus 0.706, or 0.975. So that means the vapor pressure equals 0.975 times 23.8, or 23.2 torr. If we put more glycerin in, what would happen? This number would get bigger, which means that the mole fraction of water would get smaller, and the vapor pressure of the solution would get smaller. So it would lower even more the more concentrated you made that water. The more concentrated with glycerin. And I don't know if it's glycerin with the E or glycerin without the E. I guess without the E. All right, so like I said, that last problem said that the solute was non-volatile. It gets much more complicated if it's a volatile solid, meaning that volatile solute, because what that means is both the solvent and the solute have vapor pressure, so then it gets kind of really complicated. They each will contribute to the vapor pressure, and so actually Raoult's law becomes where the P of the solution is equal to the P of the solvent times the mole fraction of the solvent plus the P of the solute times the mole fraction of the solute. So you have to include both of those because they both vaporize. So like I said, it does get very much more complicated. The vapor pressure will be of the solution will be the sum of the partial vapor pressures for each solvent and solute, and you have to add them together. This gets really, if you go on and take organic chemistry, this is really important in distilling things, and so you can separate them by a fractional distillation because the vapor pressures are going to be different. Anyway, this is a bit beyond what we're going to do in this. So our second colligative property is the boiling point elevation. So we already know from the last chapter that the normal boiling point of a liquid is the temperature at which its vapor pressure equals 1 atmosphere. So when the vapor pressure gets equal to the prevailing atmosphere, or at standard atmosphere, 1 atmosphere, it will boil. Well, remember that because you have a solution, the vapor pressure of the solution is lower if you add a solute, if you add a non-volatile solute, which again is all we're going to focus on. So what's happening is in order to get up to 1 atmosphere, we have to heat it up a little bit more. And so the temperature has to be a little bit higher to get to boiling. So the boiling point of a solution will always be higher than the boiling point of the pure solvent. So this is called the boiling point elevation, naturally, because it's elevated. So boiling point elevation is given the symbol delta TB, change in temperature boiling, change in boiling point. It's a colligative property again, and it's equal to the boiling point of the solution minus the boiling point of the pure solvent. So again, remember that it's increasing the boiling point, so that difference between the normal boiling point and the new boiling point is the delta T. How much higher is the actual boiling point? So delta TB just equals the boiling point of the solution, the temperature of the boiling point of the solution, minus the temperature of the boiling point for pure solvent. So just for example, let's say your solution of water boiled at 101 degrees. And if it was just pure water, it would boil at 100 degrees. So our delta TB is going to equal 1 degree. So it's 1 degree higher than what it would be in pure solvent. So that's how you find delta TB. So this little picture kind of tells us what's happening. So the blue line is the pure solvent. So here we have our triple point. Here we have our boiling. On this line right here is vapor and liquid at equilibrium. And so because the vapor pressure drops, the line, this line for the boiling point, or the line between liquid and vapor of the solution has gone down. Because that's gone down, this whole line has come down, and now our triple point is even lower. And so you can see here, this is what this is showing you. To get to get to 1 atmosphere here, we have to raise up the temperature. So that's what delta TB, I can't circle that, delta TB is. Can't see my cursor. We'll talk about freezing point in just a second, so we'll look at this again. So the boiling point elevation is proportional to the concentration. That's why it's a colligative property. It depends on the concentration. In this case, like I said earlier, we use molality because temperature changes will change concentration and molarity, whereas molality won't change. So this happens to be the equation for the boiling point elevation. The change in boiling point will depend on the concentration in molality. Kb is just a constant that will depend on the on whatever the solvent is. So you'll be given Kb, or you can look it up in a table. So Kb is called the boiling point elevation constant. It depends on the solvent. It doesn't depend on the concentration. It doesn't depend on the identity of the solute. Now, the change in temperature does depend on the concentration, but it does not depend on its identity. And Kb only depends on the identity of the solvent. So here are some examples. So we're just looking at boiling point here. So if we look, water is the one we know the best. So water boils at 100 degrees. If we put something in it, it should boil higher. The Kb for water is 0.512. So it would depend on the concentration times the 0.512, and then you add it to 100. So the boiling point will be higher than 100. Do note that the delta T will always be higher than the normal boiling point. So like if you were boiling acetic acid, since the normal acetic acid boils at 118, the boiling point will be added to 118.5. If you were using benzene, the Kb is 2.53, and so you would have to multiply by the concentration and add to 80.1. So delta Tb depends on the Kb and the concentration, and then what you do is you add it to the actual boiling point to see what it is. So freezing point depression works just the same way. When a solute freezes, the crystals of the pure solvent will separate out because they're not soluble. And so it turns out, because of the solid, because it's not as dependent on pressure, that part doesn't really change, but the whole thing kind of comes down. The triple point is lower because of the vapor pressure, so that line, I'll show you on the next slide, the line moves over just a little bit, and so the freezing point does go lower. The freezing point will be lowered. A solution will be lower than the typical freezing point for the pure solvent. So a freezing point of a solution is always lower than the freezing point of the pure solvent. So like I talked about here, so even though pressure doesn't really affect freezing point, because this whole line is lower than the blue line, this whole line comes down, our triple point is lower, and so in fact the freezing point, you can see this purple here, the freezing point will decrease by that much. So our boiling point will, so the purple here, we actually have liquid from this point all the way up, whoops, to that point. So let's do a different color. So if the pure water boils or freezes at 0 degrees and boils at 100 degrees, now the solution will freeze at like maybe -10 all the way up to maybe 5 or something like that. It's not proportional, but you get the idea. Or 105, sorry. So you have to add it. So that's 100. This will be 105. So it's up greater than 100. This will be less than 0. And that's if it's water. It will depend on what the solution is. But the delta TF is lowered because of the vapor pressure of the gas. So the whole thing changes. So the same kind of equation is used for freezing point depression. Delta TF is also a colligative property. So delta TF, again, this is change that color. It's the freezing point of the pure solvent minus, because it's going down, minus the freezing point of the solution is what delta T is. So, and delta T is related again to the molality of the solute or the solvent. So it's the molality of the solution times Kf, and again Kf is just found depending on the solvent in question. So same idea, you can do the same thing. So I think I've got an example. Here are again, so we had the boiling point and the boiling point constant, and then we have the freezing point and the freezing point constant. So again, if you're talking about water, pure water freezes at 0 degrees, but because if you put something in there, salt or sugar or something like that, it will freeze less than 0. It will decrease, and the Kf for water is 1.858. Okay, so let's do a problem. Let's say we have an aqueous solution which is 0.22 molal in glucose. So just a reminder, what is molality? Let's get my pen here. Is 0.22 moles of glucose. Glucose. This says mole per 1 kilogram of water. So you have to have your concentration in molal. So that's why we worked earlier to convert, because if we have molarity, we have to convert it to molality to be able to do this problem. Anyway, what are the boiling point and freezing point for this solution? So if we look at the table on the previous slide, we look for the Kb for water, 0.512. Kf for water is 1.86. Notice the units are degrees Celsius per molal. So we can find the boiling point elevation and the freezing point depression. So remember that delta TB equals Kb times N. We just looked up Kb, which is 0.512, so that just depends on the solvent, which happens to be water. And we know the concentration in molality is 0.22. So again, this problem is straightforward, but what if it didn't give you the concentration, but it gave you all the details to be able to figure the concentration? That may be true. So anyway, 0.22 times 0.15 is 0.11. Now, that is not the boiling point, right? Because what is it? Boiling point elevation. So it's going to be 100 plus 0.11. So it will boil at 100.11 degrees Celsius. So don't forget that part. So that's the change in boiling point, and then you add it to the actual boiling point. And in this case, water is 100, so we add it to 100. Delta TF is Kf times M. So this time, because Kf is 1.86 times 0.22, we get 0.41. So actually the freezing point lowers a little bit more than the boiling point does. And again, that is not this. It's pretty easy to remember that is not the boiling point, because you're like, wait, at 0.1, that can't be. You remember, but it's harder to remember the freezing point because it's so close to 0. So the freezing point is not 0.41. Remember that the freezing point is negative 0.41 because it's decreased down from 0. So negative 0.41. So these are our boiling point and freezing point. And again, if the problem doesn't give you the molality, you might have to find it somewhere.